This video in my Casting Shadows series is about shadows of spheres. The shade and the shadows tell us the type of circular form we're dealing with. An ellipse or disk has a constant value to indicate that it's on one plane, and it touches its shadow at one point. A sphere, in contrast, has gradations from light to dark, and it sits on its shadow. It has a light elliptical top whose major axis goes through the center. It has an elliptical base whose major axis also goes through the center, so that their minor axes lie on the axis of the sphere. The major axis of the shadow goes through the center of the base and a little bit beyond to account for the part of the shadow cast by the back of the orange. When the orange is flat side down, it meets its shadow at 2 points, and the major axis of the shadow goes through the center of the form. If the flat side is up, it's a little more complicated, but the basics are there. The two major axes are parallel, so their minor axes line up, and the major axis of the shadow goes through the center of the base. The terminator is a round disk in the sphere that divides the light area from the shade. It's the shade line for the sphere. But it also blocks light from reaching the cylinder of shadow, which we would see if there were particles in the air, and the shadow on the ground. Light rays hit the outer edges of the sphere at the tangent points on the terminator. While we only see 2 of them, the terminator is composed of a string of tangent points encircling the sphere that define the shadow line. The central light ray goes through the center of the terminator and the center of the shadow, and it is perpendicular to the major axis of the terminator. It's also perpendicular to these 2 sides of the terminator. When the sphere sits on its shadow, the center of its base is vertically below the center of the sphere, and its base lies within the major axis of the shadow runs through the center of the base. Now, the ellipse for the base and the ellipse for the shadow have the same proportions, that is how wide or narrow they are, because we're looking at them from the same viewpoint. Now, you could use the terminator to find the shadow if you establish a ring on the ground that accepts vertical poles from the terminator down to this ring, and then you can use light triangles to find points on the shadow. Many artists put a circle in a box in order to find the shadow of a sphere, although I think this method is excessively complicated and flawed. The box would have to be a cube in perspective enclosing the sphere, which is a whole other difficulty. How long, for example, would you make these receding lines so they look like they're the same length as the sides we see straight on? The circle would have to touch the center of all the sides where the diagonals cross. To find the shadow, go from number 1 down to 2 and then across. To find these 2 ends of the shadow, you find the green ends of the terminator and draw tangent light rays through them, and that will give you this point here and this point here. For the width of the shadow, it goes from one end of the cube to the other, and that depends on drawing an accurate cube. But most of all, it doesn't matter how wide this terminator is, you get the same shadow. And that's wrong, because the terminator is the only thing that defines the shadow. But we can boil this all down to the terminator and the shadow, because the terminator completely defines the shadow. Then it's just a matter of finding the shadow of a floating ellipse, and my spokes method is perfect for that. You set up spokes through the terminator ellipse that goes through the center of the terminator, and then draw light rays from each end of the spoke to find shadow spokes that go through the same point on the shadow. My next video is about shadows of cylinders, and please subscribe.